materials. So, this is really the key to how we do this. We're looking for production mechanical properties, performance properties, and testing to production testing standards, right? So our aim is to produce data sheets that have consistent data. So where in the past we were looking at data sheets that are essentially at the most 2 pages long, often only 1 page, that gave very basic mechanical properties, what we've been doing for quite some years now is building out data sheets with some consistent data across materials and across platform types in order to really describe as best possible. Of course, that doesn't necessarily mean we're going to have all of the data available that everybody's going to want. That's not really feasible. But largely, this covers a very wide range of applications, and often we'll be testing a material according to the kind of applications that it's designed for. Important here is that we're testing to recognize standards, so ASTM, ISO standards. Excuse me. And the important thing here is that those standards, ASTM, ISO, all call for materials to be conditioned. The data, the parts need to be conditioned for the tests, such as elongation and break, HDT. And if those specifications aren't followed very closely, that can really skew some things, particularly elongation and break, HDT, to have higher values. So it's important when people are looking at the data that they really understand that those testing standards are things that we really follow to the letter. So there's a lot of kind of nuances around some of this data that I really kind of want to make the point is that we are really ensuring that we're following a lot of this testing to the letter, and it's good to have the reassurance when comparing materials from a standard plastics handbook, for example, against what we're doing on the data sheets here, is that the data really is comparable. And it's the same for any other kind of additive manufacturing supplier. It's important to understand that what kind of testing they are doing, and are parts conditioned, for example, and are they following those kind of standards to the letter. There's lots of nuances around creating this data, which is very important. Next slide, please. So a key factor in a material being a production material is that long-term environmental UV, humidity, stability. So this means that the mechanical properties the day the parts are post-cured and finished should essentially remain within a small percentage over years, so not just days or months. So obviously in the past, the stigma is that all additive plastics are brittle in weeks. Yes, that was true. Right now, with the advent of the new materials that we're working with both projector-based machines and with SLA now, is that we are producing materials that have significant advantages in terms of indoor and outdoor stability tested to those recognized standards. And it's often a case where some of these properties will actually improve over time with these materials. So the material I've picked out here is Acura AMX Durable Natural. This is one of those new materials I was describing that is purely based on acrylate, so not an epoxy-based material. So what you see here is the stability of this material over time, and this is actually indoor weathering, indoor stability, showing how an accelerated aging test shows how the material really is incredibly stable and sometimes improving. But the one thing to note here is that when you're looking at any long-term stability testing, the one thing that really shows how stable a material is the elongation at break. A lot of the other properties for a lot of other materials don't change that much, but the elongation of break is one that will really suffer. And if you click again on this slide, please, you'll notice there's an example here of one of the older epoxy materials that really shows that elongation at break dropping like a stone after a very short period of time to a very low value, to the point where it's probably not usable for most applications. So a good kind of context there in terms of what it is that we're trying to achieve and what we're achieving now with these new materials. Okay, next slide, please. One of the other things we're including on data sheets now also is how these materials perform in terms of exposure to common chemicals and automotive fluids. That was a question that historically we've been asked a lot over periods of time. So this is essentially taking tensile parts and various other mechanical test parts, immersing them in fluids, and then testing them after various different lengths of exposure to show how good they are at resisting some of these chemicals. Now, I don't have a comparison here against some of the older legacy materials, but safe to say they perform nowhere near this level. They generally swell and soften within days, certainly not weeks. Next slide, please. So I'll just describe how we categorize our materials a little bit further, and this kind of gives you a flavor of how we're trying to spread. So if you just click all the way through this slide, I'll go through it. I'm just mindful a little bit of time here. So we have a range of materials for SLA that are generally categorized by flexural modulus, so it gives an indication as to the general property of material, but also materials that are then categorized according to what kind of loading they will tolerate, or whether they're designed for particular applications or not, and whether they are medical capable. And of course, the range here kind of describes a very good spread. If I'd have shown you here the range of materials, perhaps 10 years ago, this would be a very narrow window here. So all the way to the left here, you see AMX durable natural, which is one of the new acrylate-based materials. Anything denoted AMX is one of those new acrylate-based materials that has that additional functionality. You'll notice AMX Tough FRV0 black on here as well. The first UL94 V0 rated SLA material for large frame SLA. That would not be possible with an epoxy material. So you see here that there's a general kind of growth of this product portfolio to, again, offer more of a solution from an SLA machine than ever before. Next slide, please. This is just a quick screenshot that I did of our kind of developing web-based materials finder. So on the 3D Systems website, via the link that you see down there at the bottom right of the screen, there is a material finder that allows you to search for materials based on various different categories, whether it's a material property or whether it's by particular industry, application, technology, those kind of things. So there's plenty of variables there. I've selected here for stereolithography, which gives you the range of stereolithography materials there, but then you can also then refine down. So this is basically working off the categorization that I showed you before. And is a very useful tool in order to kind of narrow down a material choice for the kind of application that you have. Next slide, please. So just to highlight a few materials here, and these are materials that have been added into the portfolio fairly recently. I got two AMX materials on here, AMX Rigid Black and AMX Durable Natural, again, both acrylate materials. Here again, I'm highlighting the real difference is here in terms of what these materials achieve. If you look at the AMX Rigid Black window there and look at the top right picture, these materials achieve thermoplastic-like behavior. So you notice the tensile part there is necked, so there is some yield in the material before it actually achieves a break, an elongation break. And this is actually achieving a combination that's very difficult to achieve, or has been historically very difficult to achieve in the past, is something that exhibits thermoplastic-like behavior, but still has a reasonable stiffness. Normally those materials would be very low stiffness, so only suitable for a very small range of applications. Just jumping over to AMX Durable Natural, that's another acrylate-based material. This is a super, super high impact elongation material with over 80% elongation at break, which is kind of previously unheard of from an SLA material. It's a super tough, super ductile material, and very suited actually to an application that we're developing a fair bit right now for removable mandrels for carbon fiber layup tooling. Acura Composite PIV is a material that it's heavily filled with ceramic to give optimum stiffness. So you notice that by the very high flex modulus there. Ultimate stiffness. The color is very much suited to PIV testing, so wind tunnel PIV testing. PIV involves shining a very high power green laser into the airflow within a wind tunnel, and the purple essentially is designed to absorb as much as that green light as possible. So a very good example of our application specific development for the SLA solution. Next slide, please. Another couple of examples here. I picked out some, again, that are very kind of good materials for us. One that is a general purpose material, if you like. Acura Extreme probably is one of our most successful, very popular materials, and this is based on epoxy. I'm not here just to fly the flag for everything new. There are some things in the portfolio, there's quite a lot of things in the portfolio that still have a very good place and perform extremely well. If you excuse the pun there. Extreme is a material that is designed and was originally designed to produce parts that kind of, if you like, were an ABS-like material. But more importantly, this was designed to have a really low cured line width and a low viscosity, which gave really excellent feature detail and really good processability, if you like. And it was grey because the intention was this was a true kind of form fit prototyping material useful for master patterns for silicon tooling, for example. And it's just a great material. It's a very easy material to run in the machine. So it's certainly one of my favorites. Cast Pro, a material designed specifically for quick cast patterns, for investment casting, to give really stable patterns with a low coefficient of thermal expansion for that shelling process within the foundry application area. Next slide, please. So I'm just going to quickly, I've noticed we have very little time, just some quick highlights here on a couple of materials that we've launched very recently, and I've mentioned these before. Acura AMX Tough FR V0 Black is the first UL94 V0 rated material for SLA. It is exactly the same material that we have available also for our Figure 4 and our coming PSLA machine. This is an amazing material, not only for its flame retardant abilities, but also for its mechanical properties. It is a tough material rather than what we would class as a rigid material, but has a really good elongation to break over 35%, which again is kind of almost unheard of for an SLA material up until this point, till we had AMX materials. So I would encourage you to take a look at that. There is more data available if you go to the next slide. This was a material that was developed with using the team at the University of Dayton Research Institute alongside America Makes. They did a whole ton of work with us in kind of developing that formulation and testing the flame retardancy and resistance to aerospace fluids. And there's a whole blog on that on the 3D Systems website. So if you want to know more, I would encourage you to go and seek that out on the website. Last material here, and very briefly, because I want to leave some time for some questions. If you go to the next slide and the next one, please, is Acura AMX High Temp 300C. Now, this is the next groundbreaking material, again, based on that initial that acrylate chemistry. is we have a material that achieves an HDT of 300 degrees C without any thermal post-curing. So up until this point, we've been reliant on advancing the cure of epoxy materials via UV and thermal post-cure. This material requires no thermal post-cure and way exceeds any kind of HDT you would get from any of the previous materials, which is shown there on the chart on the bottom left. This is a material that is ideally suited for some of the smaller frame SLA machines. It is suitable for SLA 750, but in certain scenarios, it doesn't work that well. I'd have to be honest about that, and I'd like to be honest about that. It's suitable for kind of thin wall parts with, parts that don't change their cross-sectional geometry that quickly, that kind of thing. But something that needs highlighting here is, just that ability to achieve really high heat deflection temperatures is a groundbreaking thing. And that pretty much wraps it up from me, I think.
Perfect. In that case, I would like to hand over, first of all, of course, thanking you and Steve for the really insightful presentation. Before we come to the question parts, I will hand over to Paul Miller from Product Marketing, who will talk us through an exclusive offer that we are currently been promoting. And meanwhile, also please type in your questions if you have any. We would be happy to answer them. Paul?
Thanks, Elisa. Well, you just heard all about the phenomenal productivity, throughput, and quality that's possible with our SLA 750 platform. And we did reference some of the Figure 4 projector technology, particularly with some of their production-grade materials. It makes it really easy to build fast, small parts, and how they share some of the formulations. We do have an ongoing promotion that bundles both of those technologies. So you can choose either the SLA 750 in the single or dual laser configuration. This comes with all of the installation, startup, and training that goes along with it. Includes an initial vat fill, as well as a cart for easy unloading. And then we're bundling in with that a Figure 4 standalone printer, which includes its standard warranty and our extended service plan. Really together create a lot of value, and this bundle helps to deliver savings up to 25%. So I did want to just make sure everyone who joined us today was aware of that. We do need to receive orders by June 15th to qualify for this promotion, and we are looking for Q3 installations. There is a QR code on the slide here if you want to reach out to us to individualize this offer. I think with that, just with the amount of time we have left, let's just jump right into questions. Just a couple of questions came in today, but let me jump to this first one here. Steve, I think this one is directed at you. For the SLA 750, a lot of highlights went around speed and throughput of each build. Are there any trade-offs to part quality to achieve those speeds?
No, there's not. We do in production sometimes sacrifice some of that, but our goal with the 750 was to improve that throughput, but not sacrifice quality. So in the past, we would try to make a corner a little too fast, and so you don't keep the vectors in the line. That is not the case here. So you still get excellent sidewall quality, still in that optimal layer thickness range. So we're not sacrificing build speed for thicker layers or anything like that, which also is going to add additional stair stuffing and some rougher sidewalls typically. But yeah, we're still running 100 micron layers for most styles and very good sidewall quality.
Terrific, thank you. I do have a materials question here. Rich, I think you touched on this a little bit, but if maybe we can just reiterate, what was some of the inspiration for going back to using the acrylates, since it was one of the original material formulations or technologies used?
Yeah, good question. Things have moved on. Things kind of develop. The the state of the art around acrylate chemistry has moved on significantly since that early period in the late 80s, early 90s, which means that, you know, we're now at the point where 3D Systems has actually been working quite a lot with acrylate-based materials, not only kind of you know, for the projector-based technologies, but of course around MJP as well, for a significant amount of time now, you know, 15 years plus. Some of the stuff we're seeing for the AMX materials and the Figure 4 materials are the culmination of work that's happened over the last 7 or 8 years in designing new base monomers, oligomers, in order to kind of create that long-term stability and the additional functionalities of some of these materials. So it's really, you know, in simple terms, it's state of the art has moved on in terms of those acrylates from those kind of basic building blocks that existed in the past.
All right, this one, I'll throw it out to both of you as kind of a free-for-all here. Without divulging any sensitive customer information, can you share any experiences of using SLA for production or production applications?
Well, there's I'll go for that straight away. There's a couple of kind of sides to that, really. You know, there's a lot of use of additive, including SLA, as a tool or a sacrificial part in a production application, you know. And so one of those examples that I gave with Cast Pro was using an SLA pattern as a casting pattern that is then shelled to create a shell to cast metal into, essentially. So yeah, that essentially is a true production application where, you know, customers are using have multiple installations of SLA machines in order to create casting patterns for unique geometries that wouldn't be able to be made, you know, forged, machined, assembled in any other way, essentially. So there's that element. The direct element is a bit more kind of unique, and in some instances based around some very kind of unique industries. There are some OEMs using SLA to build parts for automotive applications, for example, or some applications. Essentially, they turn out to be applications where there are a small number of parts needed, and there are champions within those industries that are very aware of what additive is capable of, and are essentially leveraging the cost savings that they can achieve and the speed to production that they can achieve by using additive rather than traditional manufacturing techniques. And no, I'm sorry, I can't kind of share any names of those customers that are doing it.
Thank you, Rich. And then I think we just have time for one last one here. There's a question that came in. Do the lasers on the SLA 750 work individually, or do they stitch together? Steve, maybe if you can tackle that one.
Yeah, we touched on this a little bit. They work individually, so they can draw their own parts, but they also have the ability to share a part. So 2 different scenarios. You could have a platform full of small parts. It's going to automatically divide those parts into basically an equal number of vectors, and then those lasers will tackle those individual smaller parts through the layer that print. But you also have the other scenario where you may have one large part or a couple larger parts in your print. In that case, the software automatically divides up the vectors even within that part, and so when they share that part, and then one of those lasers will take on the duties of scanning the outside of that layer so that you do not see a seam. So there are no seams on SLA 750.
Perfect, thank you. Well, we are out of time here. I'm going to turn it back to Elisa to help close us out for this session. Thank you.
Oh, thank you, Paul, Steve, and Rich, for putting together this presentation. Very insightful and interactive. That was really great. And most importantly, thank you to all our attendees today. it was great having you with us, and stay tuned. I can announce that we definitely will have another webinar also on Figure 4. I know we touched on some of the materials already very lightly today, so maybe that is an interesting topic for you. And I know we have Rapid coming up for our US folks on the call or in the meeting. So please join us there, visit our booth. We are happy to see you. And interested in one of those promotions that Paul mentioned, either the single or the dual, please reach out and we'd be happy